Hi guys, in this video we're going to talk about pressure and temperature. This goes with, let's get our chrono paper out, there we go. This goes with objective 3.5, pressure and temperature, talking about the relationship and using the relationship to predict calculations. Make sure you put your name, class period, and date over here. Whoops, over here. And I've got some things pre-written here and I covered them up so I can find them easily. Okay, so our essential question is right there. How are pressure and temperature related, and how do I use that relationship to solve problems? So at this point you've done a lab where you looked at the relationship between temperature and pressure. Oops, didn't mean to make that mark. And hopefully you found that you probably started with a high temperature if you follow the directions correctly. You started with a high temperature and you gradually brought that temperature down, and you noticed that the temperature went down when you did that. And so the graph that you ended up with looked like this, which is a linear relationship, a positive linear to be more precise. And positive linear is code for the same, and that's why I've written the same right here, because they change in the same way. So what that means is that if temperature goes up, pressure goes up, and if temperature goes down, pressure goes down. This is the same as number and pressure, the number of particles and pressure, and this is the opposite of pressure and volume. Remember, if you have less space, that makes you have more collisions, and if you have more particles, that makes you have more collisions, and if you have a higher temperature, that makes you have more collisions. So these are the relationships that we're looking at now. So there is something very important when it comes to using temperature that is different than the other relationships, and that is that you have to have your temperature in Kelvin. Remember, in Unit 2, we learned that there's different scales, and that on the Celsius scale, 0 is where water freezes, and 100 is where water boils. But Fahrenheit has a different scale, and then we learned about this guy Kelvin, who took the Celsius scale and he said it doesn't make any sense to have a negative temperature, and so he decided that the lowest possible temperature that you should be able to have is 0. And what that does for us is it lets us know what the particles are doing, and we can compare things to when it's not moving. So we have to do the conversion. So this is how you do it. It's a pretty easy formula. You take your Celsius and you add 273 Kelvin. So for example, if you had 0 degrees Celsius, that would be 273 Kelvin. If you had 25 degrees Celsius, that would be 298 Kelvin. It's literally just adding 273 to any one you have. Now, now that we're talking about temperature and pressure, there's something that we talk about in chemistry, and that is called standard temperature and pressure, which is abbreviated STP. If you ever come across a problem that says STP, it means standard temperature and pressure, and in our chemistry class, we're going to use 273 Kelvin and 1 atm. So make sure you commit those numbers to memory, standard temperature and pressure. The standard temperature is 273 and standard pressure is 1 atm. Okay, so let's take a look at solving some problems, knowing that those relationships are going to be the same. So we've got this example here, and I'm going to go ahead and read through it and kind of highlight it as we go. All right, a gas has a pressure of 1.0 atm at 25 degrees Celsius. What temperature will it need to have a pressure of 2.0 atm? Okay, so I'm looking at pressure and temperature here, and I need an initial and a final, and then I can think about the change to help me know what to do. So when I put my numbers in here, I'm going to start with this pressure of 1 atm. That's a pressure. If it didn't say pressure, atm would give me a clue that it goes in the pressure column because atm measures pressure. So I'm going to put that 1 atm right here. Now it's at 25 degrees Celsius, but remember I have to use Kelvin instead. So I'm going to take my 25 degrees Celsius, let me zoom in here, and I'm going to add 273 to get 298 Kelvin. So it's that 298 that's going to go in for my temperature instead of that 25. If you put Celsius in here, you're going to have some problems especially if it says 0 degrees Celsius, because anytime you multiply or divide by 0, actually you can't divide by 0, but when you multiply by 0, you end up with 0, which might indicate that there is no change, and that doesn't make any sense. It also doesn't make any sense to have 0 pressure, so if you end up with zeros anywhere in your problem, you can know that you probably didn't change it to Kelvin. So the next question says, what will the temperature be? So I'm going to put a question mark here at 2.0 atm. So, all right, so my pressure is going up. My pressure is going up. In fact, it's doubling, and my temperature then will have to also go up. All right, so let me change to a different color. How about blue? Okay, so remember with the pressure and volume, we were thinking about what the change was and what we should do with the other numbers, and we did the same thing with pressure and number. What was the change, and what are we going to do with that information? So we're going to do the same thing here. So we're going to go with, we're going to look at how much the change is. So to get from 1 to 2, I had to multiply by 2. And since these guys do the same thing, then I'm going to multiply by 2 here. In pressure and volume, I would have done the opposite, so I would have divided, and in pressure and number, I would have done the same, so I would have multiplied also. So here I'm doing the same thing. So it's going to go from 1 atm to 2 atm. That's twice the pressure, which means I'm going to have twice the temperature. So in my calculator, I'm going to do 298 times 2, and I get 596. So 596 Kelvin is going to be my answer. I could write that over here, out of the way, 596 Kelvin. And that's going to be my answer. Now, if I had left it at 25, then my temperature would have gone up to 50 degrees Celsius, which is not twice the temperature, twice the speed. It is twice the temperature in Celsius, but that doesn't correspond to my particles moving twice as fast. In order to have twice the pressure, my particles have to be moving twice as fast. That's why I have to use Kelvin. All right, so let's look at another example. Here's example 2. It says we have a sample of gas. It has a volume of 8.2 liters at a temperature of 273 Kelvin and a pressure of 0.98 atm. What pressure will it have, excuse me, at 315 Kelvin? Okay, so same idea. I'm going to take my pressure and my temperature. This volume here is just extra information. I don't really care. Okay, that's extra. Extra. You know how in math class sometimes they give you extra information? That's what we did here. All right, so I've got a temperature of 273 Kelvin. That is already in Kelvin, so I can leave it there. I don't need to convert it if it's already in Kelvin. And a pressure of 0.98 atm. What will the pressure be at 315 Kelvin? Okay, so my temperature looks like it's going up. 273 to 315, which means my pressure has to go up. 273 is 0 degrees Celsius, and 315, what is that in Celsius? 315 minus 273, so it's going up to 42. So if I had left this in Celsius, I would have ended up with a 0 there, and that wouldn't help me at all, because anything I can't get from 0 to something else by multiplying or dividing. So now I'm going to look at the change here. So let's go with purple. Yeah, purple looks good. All right, so to get here and here, I have to do the same thing. So in my calculator, I'm going to figure out what I had to multiply 273 by to get to 315. So I'm going to take 315 divided by 273. And I get 1.15 and some other numbers. So I must have multiplied because it's bigger, right? Times 1.15. Which means I got to do the same thing on the other side. In fact, in my calculator, instead of trying to do something else, I'm just going to hit the times and use that answer with my 0.98. And I get 1.13. So 1.13 atm is my answer. Now, if I had had bars or torrs or millimeters of mercury, it wouldn't have mattered about the atm or about the pressure unit here, I would have just used the same unit over again. But I always, always, always have to have my temperature in Kelvin in order to do these problems. And these are changing the same, so I do the same to both sides. If you have any questions or you want to see any additional examples, please make sure you ask your teacher. It will help you out a lot. All right, thanks for watching.